The use of the term ordinary least squares regression refers to what we've been talking about the last couple of weeks, creating a predicted line that is the best fit line through the data, one that minimizes the squared deviations from that line. This is where least squares comes from, that term. We know that our predicted line, our best fit line, will never be perfect. All of our data points will not fit perfectly on that line, and the line will not run through every single data point in the data set. We also talked last week about what these deviations look like and how we could use them as prediction. So the error is the difference between our observed value, the value in the data set, and the predicted value, the value based on our regression line. And we talked last week about how we measured those. In multiple regression, we can also use our R-squared value, our coefficient of determination, to provide a measure of how good our prediction is. And we can interpret this to tell us about how much we reduce our error. And so we can talk about it as a PRE measure, a proportional reduction of error measure. There are three major sources of error that Allison talks about in the first chapter. The first one is measurement error. And we talked about measurement error earlier in the semester, and this isn't really something we can always control for. Not everything can be measured with perfect accuracy. Sometimes the indicators that we're using are not adequate measures for what we're trying to assess. So we need to do the best that we can by creating the best measures and carefully collecting our data. But sometimes our measures are inadequate. We also know that sampling error can be a source of error. We know that our sample is never a perfect reflection of our population. Throughout the semester, we've talked about significance levels and confidence intervals as ways to couch our language in terms of assessing what's happening in the population based on a sample alone. The entire logic of hypothesis testing is encapsulated in this, in dealing with sampling error, in recognizing the potential difference between our sample and a population. When we calculated confidence intervals, we also calculated standard error. And if you recall, the standard error is the value that gets inserted into the confidence interval equation. So it's the standard deviation over the square root of n. Maybe you remember that. When we calculate regression using SPSS, it will generate a t-value for us using that standard error value and then assess the significance of that t-value. So we get a sense of the statistical significance of our regression equation. Finally, we have to deal with uncontrolled variation. Much of the uncontrolled variation in the data come from the fact that no matter how many variables we try to include in a regression equation, there are going to be influences we can't take into account. Our equation is never going to cover 100% or explain 100% of the variation in our dependent variable. There are going to be factors, indicators, variables that we don't include that aren't part of our equation model. So it's never going to be perfect. And so there's always going to be uncontrolled variation, unexplained variation.